a square root equation or a root equation, but it has two square roots, right? So the process is, if I just have one square root, we isolate square root, square it, it gets rid of it, and we move on, right? Okay, it develops an equation that we can solve. Now let's just draw some comparisons to maybe think about what could happen here. If I had just like 7x plus 9 is equal to 6. If I square both sides, I would get 7x plus 9 equals 36, right? I get a first degree polynomial. I get a linear equation, okay? Oops. If I take the original equation, this one up here, and I square both sides, it'll give this side, it'll get that radical to go away, but it's going to keep a radical over there. And then what I have to do is square again, okay? So that ends up giving me a second degree equation eventually, okay? If I had another radical, okay, it's going to end up giving me eventually a fourth degree equation, okay, with an exponent of 4. So however many radicals you start with, this process will work. It just, after 2, it's kind of cumbersome. There's a lot of work, and then with the equation that we developed that we can actually solve, we have to have a pretty good amount of information in regards to like rational root theorem and stuff like that to be able to solve. So you're not going to, I'm trying to get at, you're not going to get anything more than 2 roots in the same equation, okay? And right now the hope is that those roots have the same index. These are both square roots, right? It's much more difficult if I have a square root and a cube root, okay? It's not too bad if it's like a square root and a fourth root, or a square root and a sixth root, or a fourth root and a sixth root, because they have those even powers. Same thing with odd powers or roots, but it's much easier if they're the same. So what we want to do, just like normal, isolate a square root. Okay, is there already one isolated there? So it's isolated, so we're going to start squaring this side. And then we'll square this side. Okay, so I square the left-hand side, I get just 7x plus 9, right? 7x plus 9. Now when I square the right-hand side, remember what the right-hand side says. The right-hand side says 6 plus radical x plus 9 times 6 plus radical x plus 9. That's what that right-hand side says when we square it, right? So what does that tell me? What's that algebra lead me to? What process? FOIL. So first times first gives me 36. Okay. Last times last gives me x plus 9. I like to do that one because that's easy. Okay. But now if I do O and I, okay, well, if I multiply those two together, don't I get 6 radical x plus 9? And then last times last, or sorry, outsides, I guess, I get 6 times radical x plus 9 again, right? So what I really get here is 12 radical x plus 9. Okay? So if we look at that equation, that new equation that we developed, it's got more terms than what we started with, but the nice part about it is how many roots are there left? Just one, right? Just one square root idea left over in contrast to the 2 that we started with. Okay? So we do know, even though it maybe got a little bit longer looking, it is simpler in that respect, that we only have one square root left over. So we keep going. Okay? Now it's just a normal square root equation. We want to isolate the square root and square again. Okay? So I'm going to move everything over. I'll get 6x over here, that 9, and that 9 will cancel out. I'll get minus 36 is equal to 12 radical x plus 9. Okay? At this stage, you've got some options. Okay? When I have a product with my square root, or even if it's division, I could just square the right-hand side right now. Okay? Or I could divide both sides and get that 12 out of there. Okay? I prefer to get that 12 out of there. It's a personal preference, but I know because in the next step, if I squared this, it's going to be 144 here, right? And then I got to do 6 divided by 144 and 36 divided by 144. I would much rather do 6 divided by 12 and 36 divided by 12. Does that make sense? Okay. So I'm going to divide that 12 out right now. So give me 1/2 x there. it's going to be minus 3 is equal to the square root of x plus 9. Okay. I'm going to square both sides now. Square that. Square that. So the right-hand side gives me x plus 9. That's easy. The left-hand side, though, remember that's FOILing again, right? So you go first times first. So 1/2 times 1/2 gives me 1/4. And then x times x gives me x squared. So you get 1/4 x squared. The next thing we're going to do is we're going to do O and I. So O and I means multiply those two things together. So you get negative 3/2. And then you double that. It gives you negative 3. So you get negative 3x. And then last times last would give me positive 9, right? Okay. So if you're struggling with this stuff here, if you're continually just getting like the 1/4 x squared plus 9 or something like that, because you're missing the O and I, write that out. Okay, there's nothing wrong with, for the sake of getting the question right, I would much rather take the 20 seconds to write that out and recognize that it means FOIL, and now I can get those correct terms. Okay. Hopefully, maybe you do that 5, 6 times, and then you realize it just becomes ingrained. I don't have to do that. Maybe I can use this technique of multiplying those two together and doubling. I'm going to move everything over to the left-hand side now because we do now have a quadratic equation. We've gotten rid of all the square roots. Okay. So I'll move the x over, so I get 1/4 x squared minus 4x. Move that 9 over, and they cancel out, so it's easier. So now, what can I do with both those? What do they have in common? X. Okay. Hopefully you start to recognize when the amount of terms tells me something. Okay. If I only have 2 terms, I can't use product in some techniques and stuff like that. 2 terms, there's probably going to be a GCF that I take out, and that GCF in this case is x. So then I get 1/4 x minus 1, oh sorry, minus 4 is equal to 0. Take that x out. So remember, this is a number. X is representing a number, correct? This is representing another number. When I multiply them together, I get 0, right? So one of those numbers, or both of them, has to equal 0. So either that is equal to 0, or that one's equal to 0. Okay. This one is so simple, I think people forget about it or lose track of it. Remember that x times 1/4 x minus 4, the product of 2 numbers is 0, so one or both those are 0. That one's it's almost trivial. It's so easy, but it's one of those things that it's so easy we make it hard and we forget it and we don't understand what it means. Okay, x is 0 here. Add 4 to both sides. Multiply both sides by 4, then x becomes 16. Okay. Now what I want to do, because remember the squaring process developed new equations, right? Okay. And the root functions that we started with, okay, do not look anything near this quadratic equation, this parabola that we developed graphically. Does that make sense? Okay. So we got to make sure that when we come back up here to the original problem, okay, let me get rid of. Clean this up a little bit. All right, so that was the original problem, right? We want to take the 2 values that we found, 0 and 16, plug them back in, see if we get a true statement. Okay? So I'll plug in 0 first. So I plug in 0 here, I get, what, 9? Square root of 9 is 3. Come over here, I'm going to get 9 again. Square root of 9 is 3, plus 6 is 9, right? Does 3 equal 9? No. Okay? So, extraneous solution. Doesn't work. Okay? And that's another aspect of this course where we have to realize when it's appropriate to check our solutions, when maybe it's not appropriate to check solutions and stuff like that. The next one was, don't want to do that. Don't want to do that either. Sorry. The next one was 16, right? So put 16. What's 7 times 16? Say again? 112? Okay. 112 plus 9? 121, right? Square root of 121 is 11. Okay? So we got 11 here. Okay? Now I come over here. 16 plus 9 is 25. Square root of 25 is 5. Does 11 equal 6 plus 5? Yeah. Yeah. So that tells me then 16 was the appropriate solution for that original picture, okay, original set of graphs. When you start squaring things, okay, this is just something we commit to memory all the time. When you start squaring things in the event of trying to find solutions, understand that you are going to develop a possibility for having extra solutions. You always have to check. Okay, there are hopefully that's not too bad to check mental math, but there are techniques if you want to use your calculator you can check as well. Any others on that assignment you guys want to talk about? So I don't have it on yet, but thank you. 36. 36. Awesome. What do you have to do when you have absolute value? If you want to start solving, don't even worry about the absolute value rules yet, but if I wanted to solve this inequality, what do I have to do first? There's the first step that we had to do with that. Say again? Okay, yeah. Okay, subtract 7. You need to isolate the absolute value, right? And that was what I was getting at. Is the same first step as what we do with those root equations. You have to isolate something. Okay. So you say subtract 7. So we get 2x minus 2. Subtract 7, I get like negative 5 over here. Okay. Now it's the absolute value, but it's the opposite of that now, right? So somebody said multiply by negative. Is that okay? So if I multiply by a negative, that'll give me positive 5 on the right-hand side, right? You guys remember what you do with inequalities when you multiply by a negative? Flip the inequality sign. So you got to do that. If you didn't do that, what would happen is that you would get the complement answers. You would get, if we're looking for an answer here between negative 5 and 5, you would get the answers that are outside of positive 5 and outside of negative 5. Okay, so less than those numbers and greater than those numbers. Here we're looking for the in-between numbers. Okay, so with this rule then, remember if we have ax plus b is less than or equal to c, that less than or equal tells us that we're looking for the value of x that will force that expression to be stuck between c and negative c, to be in between those values. Okay. So our c value in this case is 5. So we'll just go 2x minus 2 less than or equal to 5. And over here we'll plug in that negative 5. Add 2 to both sides. So, or sorry, not both sides, all 3 parts. Okay. So I get what? Negative 3 is less than or equal to 2x, less than or equal to 7. Now divide everything by 2. So we get negative 3 halves, less than or equal to x, less than or equal to 7 halves. All right, now we've isolated x, right? Okay. And all this means now x, remember visually looking at x is between those 2 numbers, right? So if I were to graph this, negative 3 halves, positive 7 halves, what we'd be looking at is that set of values. Okay? Those are the numbers, and you can pick off any one of those numbers you want to. Let's say we put 0 in. Okay, I can go back up to my original problem because zero's in there, right? Zero's just an easy number to check. I can go back up to my original problem. If I put 0 in here, what's 2 times 0? 0. So 0 minus 2 is negative 2, right? What's the absolute value of negative 2? 2. What's 7 minus 2? 5. Is 5 greater than or equal to 2? Yeah. Okay. So any number that shares this region that 0 had, or that 0 came from, okay? So anything in that region right there will provide them the exact same result of a true statement. Anything outside, so let's say I chose like 10. Come back up. 20 minus 2 is 18. Absolute value of 18 is 18. 7 minus 18 is negative 11. Is negative 11 greater than or equal to 2? No, well, that's a false statement. And we should have known that because that was a value that was not inside the region that we solved for. They're going to want you to write this in interval notation. So that's why I use the bracket there on my graph. And that's why I use the bracket there, because we have equality. So that's what we're looking for our final solution. Is that all right? Anything else you guys want to talk about? 18?
I just have a question.
Yeah.
For when it switched over to like the dependent not less than, how do you switch over to interval notation? Like when you get like your answers.
When I get down to here,
Yeah.
I like to, because you're always going to visualize this as a number line. That's what this says here. This is a number line. Think about negative 3 halves. Is that less than basically 7 halves, right? So so whatever x value we're looking for, whatever our solution is going to be between those two things. So I like to graph it. And I recognize then that this x has to, because it's between these two things, kind of in the analytical or algebra notation. So then I know that when I graph it, the line segment that I'm creating is going to encompass all the values between those. And then just to convert this into interval notation, you're just going to go left to right. First number you come across that you've graphed would be negative 3 halves, so put that first. And then the last number you run out of on your graph would be 7 halves. And now because this initially was equality up here, so then that's why we put the brackets instead of the parentheses.
Okay. And how would you change it if one way one's doing the other, you're not doing it?
Oh, okay. So you're saying, what if my solution would have looked like? Well, let's take this here. So you're asking basically the question is if I would have started with that in the inequality. If I would have started with that, we would have gone through all the same math, but the math would have shown if negative 3 halves is there, 7 halves is there, your picture would have developed something like this. Okay, now if we wanted to use equality, so we'll keep those as square brackets. So now, as a number line, what would be the first number all the way over here on the left-hand side that you're coming through on the number line? Negative infinity, so we go negative infinity. We keep going through until we are told to stop, and we stop here at negative 3 halves. So negative 3 halves needs a bracket, square one, because we wanted that equality aspect. That has to be a parenthesis. Whenever you have negative infinity, positive, it always has to be a parenthesis. Now we're going to skip over these. Okay, so skip over these values in the middle, and we get then to 7 halves. So 7 halves is the next solution, and we're going to include that one. And then you pass through, and the last one you come across would be infinity. So now these are solutions. Everything on the left over here is solutions, along with everything on the right. So the notation we use is that we're going to union those. Okay. And we'll say then basically the way we read this is that any value over here, or that is in that interval there, is a solution. Or any value that's over here, or in that interval, is also a solution. And that's what that union means as well. And what's nice, at least with doing it like this and asking that question here, is because if you did not flip the inequality symbol when you multiplied by a -1, that's what you would have come up with. Okay? And that's why it's important to flip it, because you see then, when I pair these two things up, I don't know if I can grab all that stuff, if I pair those up, it creates the whole number line, right? Okay. And that's the idea of less than and greater than and equal to and all that stuff combined. Somebody had a question on another problem, didn't they? 18? Oh, what if I don't want to do this one? Why not? All right, so kind of dumb how they write this. But I think they're playing off the understanding, and hopefully the understanding that we have, that, mine's 0.5, right? That's 0.3 repeating, right? Are those in the wrong order chronologically? If I'm on the number line, don't I come across 0.33 first? And then 0.5? So we can use our symmetric property of, basically in this case, I guess, inequalities, and we can flip this. I'm going to rewrite this as 1/3. Okay? Now I can't change the direction the arrows are pointing or the inequality symbols are pointing, so that one's still pointing to the 1/3. So it's got to point to the 1/3 there. I'm going to write that middle part, 2x minus 5, 12. And then this part here still has to be pointing to that middle expression, and then I get my 1/2. Okay? You can either do that now or you can do it at the end. I just like to do it now because I think it's stupid to write it that way to begin with. Okay? And you're going to see, and they're just playing off the fact that this is what we want it to look like, and they want to see if you know that. Okay? Because as we read this, this should be the smallest number, the next smallest number, the smallest number, the next largest number, and then the largest number in our solutions. Does that make sense? So in order from least to greatest. So now, if you just had that, okay, so cover up this left-hand side, get rid of that. If you just had that equation on the right, or inequality on the right, what would you do first? Multiply by 12. And you would do the same thing if we just covered the 1/2 up, got rid of that, you would multiply by 12, okay? I do that so on the video you can't see my hand, right? So I'm going to say cover that up. You don't really know what I'm talking about when you're watching that video again. All right, so if we're going to multiply by 12, let's just do that all at once, okay, to all three parts. So multiplying this by 12, okay, 1/3 of 12 becomes 4, right? Less than 2x minus 5, less than or equal to then 6. Add 5 to all parts, so you get 9, less than 2x, less than or equal to 11. And then we'll divide everything by 2, so we get 9/2, less than x, less than or equal to 11/2. Okay. I like this one because they do vary the notation that you have to use here then on your number line. If my number line looked like 9/2 there, 11/2 there, there'd be an open dot there and a closed dot there, right? Or if you're a person that likes to use parentheses and brackets, okay, that's what it would look like. So when I write my interval notation, talk about all those solutions. I got to start at 9/2, but not including. So that tells me I'm looking at 9/2 is 4.5. If you look at 4.5000000000001, kind of being that first number that we incorporate as a solution. And then 11/2, what this is saying is 11/2 can 100% of the time be included as a solution. And that's ultimately that 11/2 when I plug back in to that there, 11/2 is the solution, or the value of x that will actually get me 6 equal to 6. All right. Anything to the left of 11/2 will give me that 2x minus 5 to be less than 6. Does that help? Any others? Maybe time for one more. Yeah. 34. Is that like a double inequality absolute value type question? Huh? No? Okay. All on 34. Want to remember that when we read this less than one, absolute value is less than 1, it's this concept, this rule. If I start with that, which is what we're mimicking here, I want to rewrite this as, I like to write this way first. I just write exactly the same thing we started with without the absolute value bars. And then we put in that same inequality symbol, we put opposites. Okay? And the idea is that the absolute value is going to be less than 1, so we're looking for an x value that will put that expression less than 1 unit away from 0. Well, it could be 1 unit to the right of 0, or it could be 1 unit to the left of 0. So that's why we got to have this component here with the negative c value. So now I'm just going to convert this into that rule. So I'm going to go x minus 4 over 8 is less than 1, but it's greater than negative 1. And that's going to force it then to be in that range between 1 and negative 1 units away from 0. Now, just like the last one, we multiplied everything by 12, and the last one, multiplied everything by 8 here. And then add 4 to both sides, or all sides. So negative 4 less than x is less than 12. Now, in interval notation, negative 4 to 12. And that then, any value in there, any x value between negative 4 and 12 is going to force that original absolute value expression to be less than 1 unit from 0. And it could be 1 unit to the right of 0 or 1 unit to the left of 0. Let's stop there. We do have, I want to at least introduce